So till now we have been looking at problem discretization. We transform the problem from original problem, which was, let's say, a boundary value problem or a partial differential equation, into a computable form. That computable form could be a set of linear algebraic equations, linear different or nonlinear algebraic equations. The transform form could be ODE initial value problem, and now we need ways of actually constructing the solution. So I just want to draw the picture that we started with when, so we had this original problem. This original problem was nonlinear algebraic equations, boundary value problems, partial differential equations, all kinds of things that arise in modeling of engineering systems. There could be differential algebraic equations. So we have different kinds of equations that we need to solve. So this is coming from your physics. This is coming from your modeling, transport phenomena, heat and mass transfer, and so on. So this will give you a set of equations. Most of the times these equations are nonlinear, not at all amenable to constructing an analytical solution. These are in multiple dimensions and you have to solve them using some numerical techniques. Okay. So the next step was problem approximation. So we used concept of approximation theory . And we got this transform problem. This is transform computable problem. So in approximation theory we used three different tools. One was Taylor series approximation. Basically we use polynomial approximations. That was one of the fundamental tools, but of course we use also function approximations later when we talked about least squares, right. So we used concepts of approximation theory to come up with a transform problem. So here either interpolation, Taylor series approximation, or least squares. These were three basic ideas that were used to transform the problem. So I would just list them here. Is either Taylor series or interpolation. So Taylor series, interpolation, or least square approximation. So these were three predominantly used tools to transform the problem to a computable form. And now we want to attack this problem. So we are and as you could see that this problem which you started with was a partial differential equation. You ended up here sometimes with nonlinear algebraic equations, sometimes with initial value problem, ordinary differential equation. So the transform problem from the viewpoint of the structure of equations could be completely different. Okay, so it need not resemble the original problem. Original problem is a partial differential equation in space and time. Here you get an ordinary differential equation only in time. Original problem is partial differential equation in space, you just get algebraic equations, either linear or non-linear. So transform problem is completely different. We hope that if we solve the transform problem, we get something close to the true solution, not the exact solution. Now how do you attack the transform problem? That is, so the next thing is look at the tools. So I am going to talk about three different tools. Ax equal to b. I would put this as solving linear algebraic equations. This is one of the fundamental tools that we are going to use. So this tool will be used to attack this problem. Well, the other tool that I am interested is actually solving f of x equal to 0. So this is another tool which is used to solve the transform problem. Okay. The third tool which I am going to be looking at is ODE initial value problem. Initial value problems is again a fundamental block, and Euler method, Runge-Kutta method, all those methods will come under this. Here we will revisit Newton's method, we will look at its other nuances and see how you can enhance the convergence. And well, the fourth tool which is quite commonly used is stochastic methods, but I am not going to deal with this. Okay, stochastic methods, this is the fourth tool. What we expect after that, once we attack this problem with these tools or their combinations, it is not always that you will use only one tool, you might use this and this, because Newton-Raphson will require this, okay, to solve this and so on. So their combinations, and finally what comes out is the approximate solution. So this is my end result. This is my end result. So I start with the original problem. I use approximation theory, come up with a transform problem which is computable. I have only 3-4 tools with me which I use ingeniously to concoct a solution. You should get this feel at the end of the course that actually it's like a bhel puri shop, you know. You only have few things with you, okay, and with the same things you can make shev puri, you can make dahi batata puri, you can make, you know, bhel puri. So it's the same thing, it's the same ingredients, okay, and by just making mixtures you can create different dishes. The same idea is here, that we don't have too many tools, we don't understand how to solve very complex equations exactly. We just know, after all that we have done progress in mathematics, we just know how to solve Ax equal to B, we just know how to solve nonlinear algebraic equations, and all these you will realize we know how to solve this approximately, we know how to solve this approximately. So ultimately what you land up with is a third order approximation. You approximate from here to here, okay, then you try to use these tools but they themselves are approximate, okay, and then there are errors in computation because of inherent limitations of a computer. So all three combined together, okay, you get a third order approximation which you hope is the close to the reality, what the real solution is. Okay, well, there is one more approximation which I forgot. If you start with a real system, okay, so this is the real process. Or a system, when you write a mathematical model, okay, that itself is an approximation. Well, when I say that a reactor is like a CSTR, it is not CSTR, or when I say it is a PFR, it is not a perfect PFR. PFR and CSTR, these are models, these are idealized models which try to approximate the reality. So from here to here itself there is an approximation. What we formulate here we cannot solve exactly, so there is one more level of approximation. Then when you try to attack them using different tools, those tools are also approximate, okay, because all these ideas of Taylor series, then polynomial approximation, interpolation, all these again we will revisit when we are doing this, okay. So they are not going to leave us, because again many of these things are not solvable, so you go back to again Taylor series, you go back to again, and then you solve an approximation of approximation and so on. So you could say it's a fourth order approximation, and in between you have a computer which is having its own limitations. So all things put together, what you get is the approximate solution. Now this approximate solution should represent something that is happening in this problem and in the reality, and this is where your inputs as engineer or a physicist or a chemist will come into picture. You should know whether this makes sense. Oftentimes you need to actually give a good guess. You must have realized this when you are solving some of the problems numerically, which and if you don't give a good guess, the solution can be absurd. And so giving good guess is where your background in engineering or science is very, very critical. Okay, so now what we do is we have come up to this point. Now we look at A, B and C. We will not be able to get into stochastic methods. Hopefully we'll be able to cover, I'll be able to do some justice to these three tools. Okay, so let's begin with Ax equal to B. And then you might wonder, well, I have been doing this since my 12th standard, so what more to it? What more to Ax equal to B? I have been doing this for ages. There is a lot more to it. I'll at least need 8 or 10 lectures. That too we will just touch the tip of the iceberg. When you are using or when you are solving problems in school textbooks with some 2 equations in 2 unknowns or 3 equations in 3 unknowns, simple methods work. Well, the first thing that you learn is Kramer's rule, right? Now what I'll show is that Kramer's rule beyond 4 equations becomes unwieldy. You cannot use it for computer implementation. The most practical method is, of course, Gaussian elimination, again credited to Prince of Mathematics Gauss. This method is probably one of the most efficient methods of directly solving linear algebraic equations. But then again, these methods will be good if you have 1000 equations in 1000 unknowns. Once you start going into 10,000, 20,000, 1 lakh equations in 1 lakh unknowns, you have problems. Okay, you still get into roadblocks of time constraints. You can use iterative methods, and we'll talk about iterative methods. So iterative methods are you start with a guess solution and then try to converge to the close to the true solution as quickly as possible. Again, iterative methods we have to look at when you are guessing and trying to go to a solution, you should know whether you will converge or not. Okay, so under what conditions you will converge is going to be one of the main themes. There are also optimization based methods, which are again iterative methods. I'll briefly touch upon optimization based methods. And then finally, I'll also talk about a fundamental thing, what is ill conditioned systems and well conditioned systems. So how do you classify Ax equal to B? Well, it depends upon this A matrix. So we'll talk about properties of A matrix like a condition number in detail. I suppose you may have been introduced to this idea of condition number, but I'll derive the basic ideas that lead to a condition number, and we'll talk about well conditioned matrices, ill conditioned matrices. When the matrices are ill conditioned, you cannot get reliable solutions through numerical computations, and you should be aware of that, because nowadays you have tools, you just give a matrix, it will pop out a solution. You should know whether the solution makes sense or not. Okay, one is from physics viewpoint, other is from computation viewpoint. If the matrix is ill conditioned, okay, you cannot get a good solution, and you should be aware of that. Okay, so let's begin by talking about existence of solutions. When does the solutions exist? B lies in the column space of A. So there are two actually pictures, there are two geometric pictures that are typically used. I'll just use this. You should actually look at the book by Gilbert Strang. He gives very, very nice introduction to solution of linear algebraic equations. This is example from Gilbert Strang. I am just taking one simple example. which is 2 minus 1 1 1 x y is equal to 1 and 5. Okay. Now there are two viewpoints by which you can geometrically visualize the solution. Well, one viewpoint which is taught in our schools is two lines intersecting, or when it goes to 3 variables in 3 unknowns, we talk about 3 planes intersecting at one point and so on. In general, we can say that hyperplanes intersecting. So one viewpoint I would say is this, that is 2 minus 1 x y is equal to 1. This is equation number 1, and second equation is 1 1 x y is equal to 5. Okay. So this is, we would say that, well, so we draw these two lines, and this is my xy plane. This is very commonly given example. So this line is 2x minus y is equal to 1, and the other line is x plus y is equal to 5, and then this line and this line intersects at this point. This is the solution. Okay. Commonly given example means not this particular example, but intersecting lines is, or intersecting planes. So this is the solution, that's what we know. The other interpretation is, of course, the column space interpretation, which is coming from vector addition. So I could view this equation as 2 minus 1, 2 1 times x plus y times minus 1 1 is equal to 1 5. Okay. This is the second equation, and here we are not drawing pictures in xy plane any longer. X and y are coefficients by which these two vectors add to give you the third vector. So this is your vector addition. This is your vector addition. Okay, and this picture is, I will call this as, so this is row picture. Row picture becomes very, very difficult to visualize in some sense beyond 3 dimensions. Okay, but my claim is that the column picture is a little easier to visualize after 3 dimensions, 4 dimensions, 5 dimensions. We are just talking about linear combination of vectors. So here what we are saying is, we have these two vectors. We have this vector 1 minus 1, and I have this another vector. This is my vector 2 1, this is my vector 1 minus 1. Okay, and then my third vector is this 1 5. We are just trying to use the law of vector additions. Okay, and then you can complete the geometric picture by drawing the parallelogram here. So actually it's just linear combination of these two vectors gives me the third vector. Okay, gives me the third vector. And when will you be able to get solution for any right hand side? When, if you want to specify any right hand side, okay, then the linear combination of the columns should span the entire space. That means these two should be linearly independent. If these are linearly independent, all possible linear combinations of these two vectors will span R2, and then any vector. Well, there will be a problem if, suppose if this was if this was 2 minus 2, suppose I change this equation to 2 minus 2, what is the trouble? These two are vectors in the same direction, okay. No linear combination of these two vectors can ever give me 1 5, okay. So the column picture would say that equation doesn't have a solution. That is because you have one equation, you have two vectors which are aligned along the same direction. There is no linear combination which is ever going to give me this vector, okay. No linear combination is ever going to give me this vector. So now when column picture tells you that there is no solution, same thing will happen for row picture. If you take a row picture here, okay, for this changed case, you will see that there are no two different lines. See, there are parallel lines which will never meet. So 2x minus y is equal to 1 and minus 2x plus y is equal to 5. So this will be the row picture and you will get two lines which never intersect, okay. So when this picture shows that there is a problem, you cannot get a solution, the row picture also will give you a problem, there is no solution. No hyperplanes meet or no planes or no lines meet, okay. We can generalize this to any n dimensional case. We can talk about linear combinations of column giving you a solution which lies in the column space, okay, and row picture will be hyperplanes, and then the solution when it exists is all the hyperplanes meet in one point, okay. So actually line is a one dimensional hyperplane in two dimensional space, plane is a two dimensional hyperplane in three dimensional space, and in four dimensional space there will be a three dimensional hyperplane and so on, and those three dimensional hyperplanes should meet, well, difficult to visualize how three dimensional planes meet at one point, but easier to look at the column picture and talk about linear combinations of columns in n dimensional spaces, okay. So we will not get beyond a certain point here. What is important is, because all of you know this, I am just revising this very quickly. When does the solution exist? Solution exists when the columns are linearly independent, okay, and same thing is true about rows. If the columns are linearly independent, the rows are linearly independent, and number of a fundamental theorem of linear algebra is number of linearly independent rows equal to number of linearly independent columns is equal to rank of the matrix, okay. So with this brief brush up, we will just get into the solving problems using, okay. Now Gaussian elimination is something which I am not going to touch upon because I assume that you already have a sufficient background of Gaussian elimination. I have uploaded some notes on Gaussian elimination, you should have a look at those notes. I just want to compare two things here to begin with to give a motivation for methods which are more efficient. One is number of computations, that are number of multiplications and divisions that are involved. So two methods that you know for solving Ax equal to b. The first method you learn is Kramer's rule, okay. The first method that you learn is Kramer's rule. Now I am going to use this psi to denote number of required to arrive at the solution. If psi represents the number of multiplications and divisions that are required to arrive at the solution, then for Kramer's rule, psi estimated is approximately equal to, I am talking about n cross n matrix. So my concern here is A is in general an n cross n matrix where n could be large, okay, n could be 1000, 10,000 or whatever, a large number. And we have seen that these kind of matrices arise when you do, let's say, finite difference method, problem discretization of boundary value problem. A two-dimensional boundary value problem will give rise to, even if you take 100 grid points, okay, along x and y, you will get a huge matrix which has to be solved. So large matrices are not uncommon when you do approximate solution. So here it comes out to be n minus 1 into n plus 1 into n factorial plus n, which is approximately, or this is equal to, this is exactly equal to, which is approximately equal to n square into 1 minute. This is n factorial plus n. This is n square into n factorial. Okay, estimated number of operations, divisions and multiplications for Kramer's rule. I am not going to derive this, you just accept this number right now. I am just going to give you a estimate of what can happen if you try to use Kramer's rule for a matrix of moderate size, 100 by 100. Okay, if you take n equal to 100, okay, this data I have taken from Professor S.K. Gupta's book. So this is, you can show that this psi is close to 10 to the power 162. Okay, and he says that a DEC computer, DEC 1090, would take 10 to the power 149 years to solve this problem. Okay, so absurd number. So to solve a problem of 100 cross 100 matrix, involving 100 cross 100 matrix, using Kramer's rule is impossible. Okay, a computer would take, the DEC computer when he probably wrote the book was the fastest one, and then he has given this number that it would take 10 to the power 149 years. Okay, so Kramer's rule is ruled out. It's just good for, you know, 10 standard or 12 standard, whatever, wherever you learn it, and good for solving 3 equations in 3 unknowns, maybe 4 equations. If you have patience to do determinants, then. So this is not a way to go, certainly not the way to go. What about Gaussian elimination? Gaussian elimination seems to be the hope here. So in Gaussian elimination, we start with Ax equal to b, then we transform it to an upper triangular matrix Ux is equal to b prime or b cap, let's call it. We transform by elimination, we transform it to an upper triangular matrix, and then we do the backward sweep. Okay, so what is the number of operations that you need here? The number of operations that you need here is n cube plus 3n square minus n by 3, which is approximately, for a large n, which is approximately equal to n cube by 3. So n cube by 3 is far less than, you know, n factorial. So this, the reason why Gaussian elimination is so popular and is a computer savvy method is because this is one of the most efficient ways by which you can solve Ax equal to b. Okay, so that's why it is introduced right at 10 standard or 12 standard, and then you start building on it as you go into your higher grades. Okay, so now, so obviously we want to work with Gaussian elimination. Okay, and now what I want to do is, before I move to iterative methods, I want to see whether Gaussian elimination can be made more efficient. Okay, by exploiting certain structures that appear in discretization, problem discretization. So at some time back when we did this discretization, I told you that finite difference or orthogonal collocations, you know, or orthogonal collocations on finite element and so on, we get some special matrices. These are called as sparse matrices. Sparse matrices are ones which are filled with large number of zeros, and they may have some nice structures. Okay, if you exploit these structures, okay, you can come up with direct methods, or so these methods which I am talking about, these are classified as direct methods. Okay, when I say direct methods, as against iterative methods in which you start with a guess, and from the old guess you construct a new guess, and so on. Okay, like Newton-Raphson, the iterative method. Direct methods in Gaussian elimination, you don't start with a guess, right? You directly solve the problem. Okay, other variants of Gaussian elimination are Gauss-Jordan method, okay, LU decomposition. So all these are variants of Gaussian elimination, but basically the foundation is Gaussian elimination. Okay, also I have uploaded something about LU decomposition. LU decomposition is Gaussian elimination represented as, you know, sequence of two triangular matrices, triangular matrix calculations. One is upper triangular, other is a lower triangular. So you can have LU decomposition also. You can have a look at LU decomposition, but that is derived from Gaussian elimination. So the order of computations are again of the order of n cube by 3. It's not too different. Okay, so in direct methods, now what we are going to look at is direct methods for solving. When I say direct method, not the Kramer's rule, of course the Gaussian elimination. Okay, sparse linear systems are those set of equations Ax equal to b where matrix A has large number of zeros, and I want to exploit spatial structure of that matrix A to come up with a efficient solution which will significantly reduce the number of multiplications and divisions that you need for solving the problem. Okay, that is the motivation for these sparse methods. Again, in this course I cannot do a justice to sparse methods. I am just going to introduce you to sparse methods. Okay, everything is a iceberg and we just touch the tip of the iceberg. If you look at sparse method in MATLAB, there is a sparse matrix toolbox and it will list so many, you know, algorithms. I cannot cover all of them, but what is important is to sensitize you that there exists something called sparse methods, and you should try to see whether there is a nice structure in your problem which can be exploited to reduce the computations. That's what is more important. So I'm going to touch upon 3 or 4 methods and we will move on to something else. But at least this will give you a flavor of what it is. What is this sparse matrix business? Okay, so we are going to look at some things which are some matrices, some sparse matrices. This is one is tridiagonal. And block tridiagonal matrices. We'll look at block diagonal matrices. We'll look at well, in general one can talk about banded matrices. So banded matrices with only m diagonals. Okay, I'm not going to touch upon this. I'll talk about these two. Then I'll also mention about triangular matrices, block triangular matrices. So these are some nice forms. Actually, if you start looking at these forms just in a linear algebra textbook, you might wonder where do I get all these forms. But all these forms appear in problem discretization. Okay, and once we write some of these forms, you will realize where they appear and how you. So the motivation for these looking at these sparse matrices becomes clear if you look at the problem discretization methods. Okay, those will give you these nicely patterned matrices which you can actually exploit to come up with efficient solutions. Let's look at first the simplest one I would say is block diagonal matrix. A block diagonal matrix would appear a block diagonal matrix will appear in orthogonal collocations on finite elements, OCFE. A block diagonal matrix would look something like this. Well, this original equation, which is Ax equal to B, I am writing it in a block diagonal matrix form. Okay, here A1, A2 up to Am are matrices which are full. They are not. They don't have too many zeros. These matrices are typically dense matrices, not sparse matrices. But all these square zeros are actually matrices of appropriate dimension which contain only zeros. So this is a sparse matrix because non-zero elements appear along these diagonals, and then here this is a dense matrix, this is a dense matrix, this is a dense matrix, but all these are zero matrices, null matrices. So this is a huge matrix filled with large number of zeros. Only here on the diagonal you have some small sub matrices which are dense. Okay, these small sub matrices which are dense. What I have done here, x here I have partitioned here. Okay, I will talk about this partitioning very soon. And even B vector I am partitioning into B1, B2, okay. Now what are these partitions? Well, my matrix AI is actually a matrix which is Ni cross Ni. Okay, so this could be, see, this could be a 3 cross 3 matrix, this could be a 5 cross 5 matrix, next one could be a 3 cross 3 matrix. If you are doing orthogonal collocations on finite elements, on the first element you take 3 internal collocation points, next one you take 5 internal collocation points, and so on. You will get this matrices of different dimensions. Only these matrices on the diagonal are dense, because if you remember, when you do orthogonal collocations on finite elements, only variables in that small segment appear in that equation. Okay, so you have this funny structure that you will get. Well, will you get this, or you will get some overlap? Probably in OCFE you may not get exactly this structure, you might get some overlapping and you will have to do some more tricks to bring it to this form. Okay, but there are some applications where you get this nice banded structure, and then each one of them is a Ni cross Ni matrix. This vector xi belongs to Rni, so it is a Ni dimensional vector. Okay, and same is true about vector bi, which belongs to Rni. So these are subsystems, which are arranged in a diagonal form. Okay, now what do I do when I want to solve this? Well, one way is the brute force is take this entire matrix and use Gaussian elimination. Okay, I can use Gaussian elimination on this entire matrix. Okay, so what is n here? Total n. My total n is summation I goes from 1 to m Ni, right? My total n, all number of, how many number of, what is the dimension of this entire matrix? N cross n. What is n? See, these are all subsystems, I am just adding them. So the entire matrix, this entire matrix is n cross n, where n is equal to summation of all Ni. Okay, these are Ni subsystems which I want to solve together. So if I use Gaussian elimination here directly, then the number of multiplications and divisions if I use one without trying to exploit the structure of this matrix, if I try to use blanket Gaussian elimination, then number of divisions and multiplications, we just listed this, will be n cube plus 3n square minus n divided by 3. The other option is I could solve subsystems. So I could solve for ai xi is equal to bi, I going from 1 to m. I have this m subsystems. Okay, I could solve each small sub problem. Okay, see this is 3 by 3 or 4 by 4, or each one of them is a smaller dimensional system. I can solve this each one of them using Gaussian elimination. Okay, now what is psi I? What is psi I here? That will be ni cube plus 3 ni square minus ni by 3, right? So this ni are 3, 4, 5, these are smaller dimensional matrices, whereas this one, this matrix is a large matrix. This matrix is a large matrix which has large number of rows and columns. So instead of using a Gaussian elimination on entire one, if I do this trick of solving each subsystem separately, then the total number of this thing is sigma ni cube plus 3 ni square minus ni by 3 is actually far less than, this will be far less than this, because see what is n? N is summation ni cube will have lot many terms than, okay. So this simple trick of identifying sub blocks which are dense and solving those sub blocks, okay, can actually reduce your computations multiple folds. Okay, so within Gaussian elimination also, if you are instead of solving one giant problem in which there are lots of zeros and you are going to waste time in eliminating zeros because there are already zeros in what do you do in Gaussian elimination? You first make it load upper triangular matrix, so you have to bring zeros, and then if you just apply Gaussian elimination without thinking, you will waste time in bringing zeros from zeros, doesn't make any sense, and but the computer will just do computations without understanding that there is a zero there. So you have to tell the computer, well, there are zeros, don't worry about those zeros, just do these subsystem calculations, and then you can solve the problem much more efficiently than, okay. So this is very important, particularly when you have iterative calculations. Suppose you have to solve Ax equal to b kind of equations inside a Newton-Raphson where A has this banded structure. Then just imagine. See, when you are doing this repeatedly, say 1000 times or 10,000 times, well, you better solve it efficiently. Okay. So suppose this Ax equal to b, this banded structure appears inside a loop. Okay, iterative loop. Okay, each time if you do these many calculations, that is much more expensive than doing these many calculations. Okay, that's where this banded matrix structure helps. Well, the next one we are going to look at is the Thomas algorithm. Okay, so the Thomas algorithm is for a special case of Thomas algorithm. Maybe some of you have done this in your undergraduate because it is often taught. So Thomas algorithm is for block, is first for tridiagonal matrices. Okay, I am going to write this notation, I am going to change a little bit here. The right hand side, these elements I am going to call them as d1, d2, dn. My matrix is now going to be written with b1, c1, 0, then a2, b2, c2, 0, then 0, a3, b3, c3, 0. So this is a tri-diagonal matrix. You have zeros here, and then finally you will get an bn. So you have this b1 b2 b3 up to bn, that is the main diagonal. Okay, there is one more diagonal above this which is c1 c2 c3, and one more diagonal below this a2 a3. So this starts from a2, this starts from 1, but this ends here at cn minus 1, and this starts from a2 ends in n. You have seen this kind of a matrix, finite difference method. You have seen this kind of a matrix. Okay, so in finite difference method you get this tri-diagonal matrix. Okay, and then question is can I exploit the spatial structure this has so many zeros, filled with so many zeros? How many elements are non-zero? Three n minus 2, n elements of diagonal, n minus 1 of first diagonal above, and n minus 1 of first diagonal below. So 3n minus 2 elements are non-zero, rest all elements are 0. Okay, so I am going to do simple Gaussian elimination here. Can you do it? Can you try this? How will you do Gaussian elimination? You should just eliminate. I don't have to do Gaussian elimination for these elements here. I just have to eliminate A2. Okay, when I come here I just have to eliminate A3. Okay, and so on. So I just have to eliminate one element below the diagonal, main diagonal. Okay, that will give me a upper triangular matrix, and then I just go on doing in the backward sweep. So if we just write the steps here, it will be something like this. So I am going to define this gamma 1, which is C1 by B1. I am just writing it algorithmically. What I am doing is basically Gaussian elimination. Okay, and gamma k is equal to Ck Bk minus Ak gamma k minus 1. This is for k equal to 2, 3 up to n minus 1. Then I have this beta 1 is equal to d1 by b1, and beta k is equal to dk by dk minus ak beta k minus 1 bk So what I have written here, it looks probably at the first sight little complex, but all that I am doing is eliminating one element below the diagonal. Okay, and these gamma and beta are the elements which appear in the. So what I am doing is, after doing these operations, I am going to get this new matrix which looks like this. This new matrix after doing all this will look something like this: 1 gamma 1 0 0 0 1 gamma 2 0. Of course, you have this matrix X here, vector X here, and the right hand side is beta 1, beta 2, beta n. These equations written here are for computer implementation. You can put it in a for loop and just do calculations. to get this matrix. These are the steps of Gaussian elimination written in an algorithmic way so that you can put it in a computer program too. So now I get this matrix, this is upper triangular matrix. When you do upper triangular matrix here, you just have to worry about one row above the diagonal, right? And now what you do? Backward sweep. Okay, you do backward sweep, you get x1 directly from this, x2 you get, right? All of you know back substitution. So now I do backward sweep and then solve the problem. What is the number of multiplications and divisions that are required in Thomas algorithm? This is called Thomas algorithm. Now I will do backward sweep on this. Should I write those equations or you are clear about it? I think all of you know about this, right? How do you solve from this? It's very, very simple. Okay. What is the point to take home is that number of multiplications and divisions for this case reduced to 5n minus 8. This is just linear function of n as against cubic function of n. If I were to use Gaussian elimination without thinking about the structure, I would be doing n cube by 3 calculations roughly. Here I just do 5n minus 8, significantly lower than what I need to do as, by normal Gaussian elimination. So Thomas algorithm is one example where you significantly reduce the computations required by exploiting the structure. The next what we are going to see is of course a simple extension of this is, if you have this, I will do in my next class, is what if, see here we have looked at this algorithm where A, B, C are scalars. What if these are matrices? What if B1 is a matrix, C1 is a matrix, A2 is a matrix, B2 is a matrix? Those matrices are called as block tridiagonal matrices. Okay, block tridiagonal matrices. So we just simply extend this idea to block tridiagonal matrices, and still we can do much less computations than doing solving the entire thing. Okay, so that's what is going to be the next extension. So these are some of the well-known sparse matrix algorithms, and you can significantly reduce the computations even in Gaussian elimination. We are still doing Gaussian elimination, we are not graduated to something new. Okay, so we will continue on more of this in the next lecture.